Imagine yourself on a beach. The waves crash rhythmically. Up and down, they move with energy. Now, imagine these waves are not water but tiny particles like electrons. Strange, right? This is the world of quantum mechanics. In the quantum world, particles behave like waves. Schrodinger's equation helps us understand this weird behavior. It's like a magic-looking glass, revealing the secrets of the quantum world. Erwin Schrödinger, a brilliant physicist, gave us this amazing equation. His work revolutionized our understanding of the quantum world. It's like a mathematical recipe, a set of instructions that tells us how particles behave at the quantum level. It tells us how these particle waves behave, how they move and interact with each other. Don't worry, we won't delve into the complex maths here. Instead, let's focus on the fascinating concepts. Think of it like this. Imagine a speck of dust dancing in a sunbeam. It moves unpredictably, just like particles at the quantum level. You can't really know its exact location, only where it's more likely to be. This is the essence of quantum mechanics. Schrödinger's equation helps us calculate these probabilities, giving us a deeper insight into the behavior of particles. By understanding these probabilities, we can predict how particles will act in different situations, opening up a world of possibilities in quantum physics. Imagine you are searching for Nemo, the clownfish, but this time it's not just the vast ocean you have to explore. Instead of the ocean, he's lost in the mysterious and mind-bending quantum world, a place where the rules of classical physics no longer apply. Schrödinger's equation is like a treasure map, guiding us through this strange realm. However, this map doesn't pinpoint Nemo's exact location. It's not as simple as finding an X that marks the spot. Instead, it shows us areas where he's more likely to be, much like a heat map indicating probabilities. These areas are called orbitals. They represent regions in space where the probability of finding Nemo is higher. Unlike fixed paths like planets orbiting the sun, these orbitals are more fluid and dynamic. Think of them as blurry clouds where the chances of finding Nemo are high but never certain. The quantum world is full of surprises and uncertainties. Section 4. Energy levels, like a stairway to particle heaven. In the quantum world, energy levels are like steps on a staircase. Each step represents a specific energy state that a particle can occupy. Just like you can't stand between steps on a staircase, particles can only exist at specific energy levels. They can't be in between these levels, just like you can't float between steps. Schrödinger's equation helps us calculate these levels. Imagine a flashlight. This equation is fundamental in quantum mechanics, allowing us to predict where particles are likely to be found. It can be on or off, but not in between. Similarly, particles can be in one energy state or another, but not in a state that is in between. Similarly, an electron can jump between energy levels, but it can't exist between them. This jump is instantaneous, and the electron never occupies the space between levels. This is why atoms emit or absorb light. When an electron jumps from a higher energy level to a lower one, it releases energy in the form of light. They do this when electrons jump between these energy levels. The light emitted or absorbed corresponds to the energy difference between the levels, creating the beautiful spectra we observe. Schrödinger's equation is a powerful tool. It unveils the strange and beautiful world of quantum mechanics. It helps us understand the universe at its most fundamental level. From lasers to transistors, many technologies today owe their existence to our understanding of this amazing equation.